Hi everyone, this is our 16th lecture as far as I recall. And we mainly talk today about k-means, but in fact we'll talk about a lot of other things surrounding it. Specifically, we'll recall maximum likelihood estimation of Gaussians, which we already covered, and we'll consider Gaussian mixture model that comes out of MLE for Gaussians, basically follows from it. Then we'll talk about clustering a little bit in general, what it is and why it's interesting. And then we'll consider one specific clustering algorithm, hard k-means. You'll understand what it means when we go through this. And another version of it, which is called soft k-means. Okay, let's go. MLE for Gaussians. Remember the continuous features? When we have our continuous features in our maximum likelihood estimation lecture number 9, and we didn't want to or didn't know how to deal with them at first. But then it was easy, right? Let's formulate our likelihood and then let's maximize the likelihood. If we model our likelihood as a Gaussian, it becomes quite easy. We will, as in any maximum likelihood um, problem, we'll need to find parameters that maximize the probability of observed data. And we do that through maximizing, we'll find those parameters through maximizing the likelihood, which is easy to do, assuming independent draws, then our likelihood factors into product of individual likelihoods, uh, likelihood of each sample independently, and then we know what it is because we said it's a Gaussian, and the Gaussian has an unknown mean parameter and a known variance parameter. But since the samples are IID, we can just consume this product inside of the exponent and proceed estimating maximum likelihood estimator of the mean of this Gaussian, which is well-known sample mean, just the sum of all of the parameters divided by n, and also maximum likelihood estimator of the variance, which is a square sum of all of the differences squared between the mean, the estimated mean, and the sample. Well, also recall that we learned that this maximum likelihood estimator is biased. So, and it's biased mainly because we are using our maximum likelihood estimator for the mean, not the true mean. If we were using the true mean, we would have been fine. So to correct the bias in the maximum likelihood estimator, we need to normalize by n minus 1, not n. Yeah, so that was good and nice and easy when we have one single Gaussian and a bunch of data sampled from it, and we just need to estimate the parameters of that Gaussian. But what happens if there are multiple Gaussians?